Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. The rate of nucleophilic addition to a carbonyl compound depends on two main factors. 1. The electrophilicity, positive character, of the carbonyl carbon, and 2. Steric hindrance around the carbonyl carbon. Greater electrophilicity and lesser steric hindrance both increase the rate. Moving on to the next step. Analyze compound A, p-nitrobenzaldehyde. The nitro group is a strong electron withdrawing group, EWG, at the para position. It withdraws electron density from the ring and hence from the ChO group via resonance and induction, making the carbonyl carbon more electrophilic. Among all the compounds, this has the highest reactivity toward nucleophilic addition. Moving on to the next step. Analyze compound B, benzaldehyde. No substituent on the ring. The benzene ring conjugated with ChO slightly deactivates the ChO compared to aliphatic aldehydes, but benzaldehyde itself is the reference aromatic aldehyde here. It is more reactive than the methoxy-substituted analog, but less than the nitro-substituted one. And for the final step. Analyze compound C, p-methoxybenzaldehyde. The OMI group is an electron-donating group, EDG, via resonance, which donates electron density into the ring and onto the carbonyl carbon through the conjugated system, reducing electrophilicity of the carbonyl carbon. This makes it least reactive among the aldehydes. Analyze compound D, methyl ethyl ketone, CH3-CoEt. Ketones are generally less reactive than aldehydes toward nucleophilic addition due to I to alkyl groups donating electron density to the carbonyl carbon, reducing electrophilicity compared to aldehydes which have one H and one alkyl aryl and 2 slightly more steric hindrance than aldehydes. However, aliphatic ketones are more reactive than aryl ketones because aryl groups delocalize the carbonyl's positive character through resonance. Analyze compound E, phenyl cyclohexyl ketone, cyclohexane ring with C is equal to O pH. This is a diaryl arylalkyl ketone with significant steric bulk, cyclohexyl group, and the phenyl group conjugated with the carbonyl, reducing electrophilicity. Both steric and electronic factors reduce reactivity. This is less reactive than the simple aliphatic ketone D. A. P-No2C6H4 ChO, highest reactivity, EWG plus aldehyde. B. C6H5 ChO, second, aldehyde, no substituent effect. C. P-Neo C6H4 ChO, lower than B, due to EDG reducing electrophilicity. D. CH3-CoEt ketone, aliphatic, moderate steric, less reactive than aromatic aldehydes but more reactive than aryl ketone. E. Cyclohexyl CoPH, least reactive, large steric bulk plus aryl conjugation. Weight comparing B, C, and D aromatic aldehydes versus aliphatic ketones. Aldehydes are generally more reactive than ketones. So, B, D, and C, though deactivated, is still an aldehyde, so C versus D is the key question. P-methoxybenzaldehyde, despite the EDG, is still an aldehyde. The OMI group reduces reactivity compared to benzaldehyde, but a strongly deactivated aldehyde can still be more reactive than a ketone or less reactive. Given the answer is A, B, C, D, E, the order places C above D, meaning even the electron-donating methoxy group doesn't reduce the aldehyde below the aliphatic ketone reactivity. Then D, E, because D is an aliphatic ketone while E is an aryl ketone with greater steric and electronic deactivation. Therefore, the order is A, B, C, D, E, which corresponds to answer choice A. Why other options fail? Option B. ABDCE places D above C, but C is still an aldehyde and should be more reactive than ketone D. Option C. ADEBC incorrectly places ketones above aldehydes B and C. Option D. ABEDC incorrectly places aryl ketone E above aliphatic ketone D. Therefore, the correct answer is A. Therefore, the correct answer is option A.